Okay, so today we're going to wrap up the 5 different types of chemical reactions. We have already talked about the first type of reaction, which was, let's get down there. This one, the reaction type number 1, in case you forgot, that was called the single replacement reaction. Notes for that are posted on Google Classroom. Reaction type number 2 was the double replacement reaction. We did that one yesterday. Reaction type number 3 was the synthesis reaction. We did that yesterday, and I also posted filled-in notes and a video for that on Google Classroom as well. So that was your synthesis. And then lastly, we're going to talk about reaction type number 4 and reaction type number 5 today. I'm going to skip ahead and do reaction type number 5 first because I think reaction type number 4 is more fun. So we are going to start with a reactant known as H2O2. I'm going to go grab that so you can kind of take a look-see at it, and we'll go from there. Okay, so this is the reactant for reaction type number 5 that we're going to use as our demonstration today. This one happens to be something that's H2O2, which is also known as hydrogen peroxide. Okay, now our before observations for this are just like what we've been doing in the past, H2O2. So our before observations, you could probably make the observation. Technically, it's a solution, but in this case, I'm going to tell you it's a liquid. This one's going to be a liquid because it's pure-ish hydrogen peroxide, even though it is dissolved in water. What else could you tell me about this particular reactant? Transparent, agreed. Not here. So I would agree that it is transparent. Yep. Colorless. And I'm going to, I would say that it falls in the category of odorless. So it's known as hydrogen peroxide, and you probably have had some in your medicine cabinet or something like that. I'm going to go back to the lab station back there to finish up this part of the demonstration. So we've identified that, yes, this is a hydrogen peroxide. It's normal, average, ordinary hydrogen peroxide. It came from the Top Care facility, which is basically Roundy's generic brand. It's known as being 3%, but we're going to pretend it's not 3%. We're going to pretend it's all hydrogen peroxide. What I'm going to do is I'm going to add something to it. I'm going to add something called potassium hydroxide to it. Potassium hydroxide is known as a catalyst. And in biology, you learned that a catalyst was something that speeds up a chemical reaction but gets the same result at the end, just makes it faster. It doesn't change anything about the reaction. It just makes it go faster. Hydrogen peroxide, on the other hand, is pretty nasty stuff. When your body naturally makes hydrogen peroxide as part of a metabolic process. The problem with hydrogen peroxide inside your body is it tends to attack your cells. And when it attacks your cells, it tends to break them down. So your body has developed a mechanism to prevent that from happening. It breaks it down into water and oxygen. And we are going to do the same thing here. We are going to mimic that. So this is potassium iodide. It's going to be the catalyst. Now, the next thing I want to point out is if you have ever been a person who has had a surgery or had a very, very large wound, and the doctor or the nurse put a giant amount of iodine on your arm or wound or whatever, what color was that ish? It was like this yellow brown, right? There's iodine in potassium iodide. And because there's iodine in potassium iodide, when it goes into water, it's going to change, when it goes into the hydrogen peroxide, the iodine itself, when it separates out, is going to change. It's going to its color is going to show through. That doesn't mean that the hydrogen peroxide has actually changed color. It's just the iodine that's dissolving out. Does that make sense? So when this color change occurs, it's not going to be as a result of me adding this. It's just that the iodine is present. So when I go to add this, okay, so right now, hopefully what you can see is that there something that's obvious to observe. Okay, so obviously you have all noted that there was a gas being produced. You saw the bubbles, right? And there is a test that we can do to identify what type of gas is being produced. So what I'm going to do is I'm going to go ahead. He's here now. Oh, no, I do. So what I'm going to do now is I'm going to take a burning splint. Please pay attention, okay? I'm going to take a burning splint. I'm going to blow it out, and it's going to be a glowing splint. And when I put the glowing splint into this test tube, watch. I can do it again. I just need a second, okay? So if you didn't see it, I'm going to do it again. I blow the splint out. And it reignites the splint. Now, let's think about that for a second. In terms of what's present as the reactant, H2O2, what potentially could cause something to reignite? Oxygen would be the one. What? Well, think about it. Oxygen is something that we need to burn, right? Oh, yes. Right. So now the next thing I'm going to do is I'm going to reignite it, and now that it's reignited, I'm going to take the burning flame and put it in there, and I want you to note that it gets brighter, okay? Did you see that it got brighter for like a very brief instant? Now, there's a reason why it doesn't continuously get bright. I'm going to do this again. Okay? And one of the reasons why it doesn't continuously get bright is because it's eating up all the oxygen as part of its reaction. Does that make sense? So that is reaction number 5, and we're going to talk about that a little bit more as I go back up to the front of the room. So as we just talked about, we talked about the fact that one of the things that was definitely produced was oxygen, and it was a gas. Okay? So at this point, in terms of products, I've got oxygen, and we've already decided that it's partly going to be a gas, okay? And what do we know? What else can we say about oxygen in general in terms of its properties? It's colorless, and I heard clear, so I'm going to assume that you are using your words and your meaning transparent. Oxygen tends to be odorless. Okay, now looking at what you have left in the formula for H2O2, what else could be a product? Hydrogen could be part of what else happens to be the product. Yeah, water, for sure. So in this instance, what happens is that catalyst, we're going to talk about a catalyst a little bit more in detail, is going to produce water as well as its product. Now, in this case, water is a little bit harder because it looks like it might be a color of yellow. But we have to understand that if we took that solution, right, and we took that solution and we boiled off all the water and we collected all the water would probably, first of all, it would be liquid because it would be pure water. It would probably be colorless, and it would be transparent. Now, so this water is going to be a pure water here. So a couple of things that I want to go back and touch upon. The first thing I want to touch upon is what a catalyst is, right? So a catalyst is a substance that speeds up a reaction without changing the results. And many times the catalyst can be recovered. And what I mean by that is in industry, a lot of times we can use the catalyst platinum. Platinum is a metal, and if you take that metal and you dump it into certain chemical reactions, it makes the reaction go faster. And if it makes the reaction go faster, and when the reaction is over, you just pull that metal out, and the metal hasn't done anything other than make the reaction go faster. In the case of this example, the catalyst, which we said was potassium iodide, I'm trying to write it over the arrow because that's how we indicate that a chemical reaction has a catalyst in there. If I wanted to recover the potassium iodide, what I would do is I would simply boil off the remaining water and be left with a crystalline powder, which in this case would be the remaining potassium iodide. The other thing that I kind of want to highlight here is the Splint test for oxygen. Okay. Now, in the Splint test for oxygen, we took a glowing splint, and in the presence of oxygen, it reignited. I think I spelled that very wrong. A glowing splint in the presence of oxygen reignites. Okay, that's the Splint test that proves that oxygen is being produced. Now, we're going to have to draw this thing. So here we go. Here's our reaction. Okay, we have to balance it first. And in this case, our reaction only has H's and O's. On the reactant side of the equation, there's 2 hydrogens and 2 oxygens. And on the product side, there are 2 hydrogens, but there's, look what's happening here, 3 oxygens. Now, I know that this particular reaction can sometimes be a little bit of a humdinger to balance, so I'm going to kind of cheat a little bit and help you out right away by saying that I know that in order to make this balance, I need to put a coefficient of 2 here, which is going to give me 4 oxygens and 4 hydrogens. In order for me to balance my hydrogens, I'm going to put a 2 here. So now I've got 4, which gives me 2 at ease, and so now I've got 4 and everybody's happy. This one can be a humdinger for some students. So just like we've done in the last couple of lessons, we did not we can't show state of matter when there's a coefficient of 1, so we're going to have to double them all. So this is going to become 4, this is going to become 2, and this is going to become 4. And then we're just going to draw our situation here. So we've said that the state of matter of hydrogen peroxide is going to be liquid. So our hydrogen is going to be a triangle. No, let's make it a square. And our oxygen is going to be a circle, I think, to make our lives a little bit easier. Now I have to draw 4 units of H2O2. And when I draw my 4 units of H2O2, I have to keep in mind that I'm going to alternate shapes so that they don't, like the same shape isn't really touching each other. So that would look something like this. And so remember my first unit, I'm going to bond together like so. And now I'm going to try my very best to kind of like show that they are connected or touching rather, but not necessarily organized. Ooh, that is a very tiny oxygen. I got to fix that. Let me make that oxygen a little bit better. That doesn't seem fair. Okay, so now, and then I'm just going to continue doing that. So in this instance here, I might have square, another square. I'm not 100% sure what this shape is. Sorry about that. Also, gosh, squares are super hard apparently for me today. And then I need to add my oxygen. So I might have an oxygen here and an oxygen here, and they're going to be bonded together. Right. And then I got to do one more. So I'm going to do something that looks like this. Square, square, throw a couple oxygens up in there, and then connect them like that. Okay. So now we have this unorganized but touching situation. We've already said that oxygen in this instance is clearly a gas because it makes bubbles. So I'm going to draw that real quick once and make sure that they're connected. And then the water I mentioned was going to be a liquid. So we'll draw that again, just like the other ones. And so in this case, I've got H2O. So I'm going to do this. And again, with my liquids, I'm trying really hard to show that they are touching, but they are disorganized. So that's reaction type number 5 in terms of a model of matter diagram. Note, I didn't add any water as X's because we're dealing with everything as a pure liquid here. So we're going to move forward. Now, with a decomposition reaction like this, you always start with just one compound. And that's it. That's all you start with. And so the generic reaction or reaction template for this situation is going to simply be Y will separate, decompose into A plus Y. Now, they're not always going to be nonmetal and nonmetal or covalent, or they're not going to always be metal and nonmetal or ionic compounds. So I'm going to try to not specify that this time around, but I am going to say that if I take my parts here and I just kind of match them up with my template, I can follow along here. Now, I'm going to have my handy-dandy periodic table out, talk about this and how this goes about. In this instance here, I'm going to take what element is under the letter A, which in this case is sodium, and I'm going to put sodium under the letter A. And the next thing I'm going to do is, once I'm looking at my handy-dandy periodic table, I'm going to locate the area where I wrote down the Brinkelhoff diatomic molecules, or the hydrogen and the super 7 diatomic molecules, and I'm going to figure out, does this element, in this case sodium, fall into that category? Sodium is right here, and sodium is not a hydrogen, H2, nor is it an N2, O2, F2, Cl2, Br2, or I2, so as a result of that, I'm just going to write it as it is. I'm going to bring this N across and put it underneath the Y, and then I'm going to do the same thing. I'm going to locate N, and I'm going to say, is it an H2? No. Is it an N2? You better believe it is. So now I'm going to have to write it as an N2. Okay. Note, I didn't bring the subscript of the 3 across because that's not how we did this. I just grabbed it as it came off the periodic table. So I couldn't make Na3 on the product side. Now, the last thing we need to do here is balance this particular one. And so I have Na and I have N. And on my reactant side, I had 3 sodiums and 1 nitrogen. On my product side, I have 1 sodium and 2 nitrogens. And I know that this one, by simply looking at it, if I balance my sodiums first, which you totally can, I can predict that I'm going to have to unbalance or rebalance later. What that means is I'm going to predict that I'm going to balance my nitrogens first in this case by putting a 2 in front of the Na3N. the sodium nitride. That's going to give me 6 sodiums, and it's going to give me my 2 nitrogens. So I'm going to balance my sodiums by putting a 6 here and leave my nitrogens alone, and so now everybody's happy. So far, so good. So that's reaction type number 5. It is decomposition. Now we're going to do reaction type number 4, which I think is the most fun one of the day, personally. Ready? Going to mosey back up to reaction type number 4, and we're going to locate the C6H14. C6H14, I'm going to tell you right now, is hexane. And I'm going to go grab that, and then I'm going to have you guys take a look at it right now. Okay, so this is the hexane right here. And as you have already noted, it looks very similar to all of the other things that we've almost all of the other liquids and whatever else that we worked with. I'm going to tell you, though, for sure that it is a liquid. So I'm going to put an L up here. I'm going to also agree that it is colorless, that it is transparent, and the question is, does it have an odor? It definitely does have an odor, so I'm going to say that it has a pungent odor. No. Now, I'd like to do a little bit of a sidebar here. Gentlemen, the number of the gentlemen in this building, and I use that term very loosely, who wander into the male bathroom and exclaim something like, "Oh, it smells like somebody took up." Guess what? That's what happens in the bathroom. People use the bathroom. They poop in the bathroom. Nobody needs to hear that you think that the bathroom stinks. Everybody knows it does. As long as we're having this conversation, let's class it up a little bit. If you want to exclaim something, why don't you say, "Hey, gents, there's a pungent odor in the bathroom," instead of "it smells like." It's not even a use the bathroom. It's as you walk by and you hear the kid exclaim so loud. Do me a favor. Take a look around. Make an observation of the other reactant. What's the other? The other reactant is oxygen. Take a look around. All right. Oxygen is a gas. Oxygen is colorless. It is transparent. And we're going to say that it is odorless. Time to get serious, people. So our clear, colorless, pungent odor liquid of hexane, right, is going to react with the oxygen in the air. When it reacts with the oxygen in the air, like, actually not much happens. So we need to give it a little bit of a push. We need to help it out a little bit. And the push that we are going to give it is just a little bit of energy. So let me set this up for you.
Whoa. That's crazy. You should touch it. You should touch it.
I'm not going to touch it.
The computer.
It's in the general area. It's fine.
Can I go up there and take a picture?
Absolutely not.
I got it. Take a picture of it.
That's a good picture, bro.
I mean, like,
That's a good picture.
so
Send that to me.
as long as we're having this conversation, which really isn't as much of a conversation as me just talking to you, note that I didn't start the building on fire. Okay? So let's talk about why I didn't start the building on fire. Because this tabletop isn't completely and totally fireproof. I can burn it. Okay? So why didn't the table burn?
Because it's ceramic.
It is, but I can make this burn. It's what's referred to as fire retardant. That means that it will burn. It just isn't. It will take a lot longer for it to happen. Does that make sense? Okay. So the truth of the matter is that I can make this burn. Okay. Why did the hexane burn, but not the tabletop? You are actually when you say it evaporated, you are a lot closer than you think. Looking at our chemical reaction, C6H12 or C6H14 plus O2, the only thing that was burning was the hexane and the oxygen. That's it. Nothing else was burning. Yeah, so the only reason why, one of the only reasons why the rest of the stuff didn't burn the table and whatever else is because the only fuel that was being consumed was the oxygen and the hexane. Okay? Yes. I am a trained professional, so no, that has never gotten out of control. Now, so, no. All right. So C6H14 would be awful to draw. But because we're talking about a very specific type of reaction called a combustion reaction, we're going to use a different hydrocarbon, and we're going to work through it. So in this case, we have CH4, which is methane, which is the gas that comes out of the gas jets that lights the burnt that runs the Bunsen burners. It's also in a lot of cow farts. So be aware. Now, when we go to balance this particular reaction, because we are definitely going to have to do that, I'm going to start by looking at the relationship between the carbons, the hydrogens, and the oxygens. On the left-hand reactant side, I have one carbon, I have 4 hydrogens, and I have 2 oxygens. On the product side, I have 1 carbon, 2 hydrogens, and look what's going on here, 3 oxygens. Okay. When I go to balance this, let me go back up. We didn't talk about products. I got ahead of myself. Products. Obvious products were things like light, heat, fire, right? So those things would all fall under the category of what word? Starts with an E. Energy, right? So in this reaction, we produce a bunch of energy, and we also produce carbon dioxide and the water. Okay? So that's a thing. Now, let's go back to this. So we're going to balance this reaction here. Starting from left to right, my carbons are balanced, so I'm going to leave them alone for now. My hydrogens are not. So I'm going to add a coefficient of 2 here, which will give me my 4 hydrogens. It's going to have 2 oxygens there, 2 oxygens there, which gives me 4 oxygens on my product side. I'm now going to go ahead and put a coefficient of 2 here to get my 4 oxygens on my reactant side. And when I leave it like this, we have to go back to the idea that we're going to double things because we have coefficients of 1. So in this case, I have a 2, a 4, a 2, and a 4. Methane, CH4, is a gas. Oxygen is a gas. Now, true story. Carbon dioxide, definitely a gas. Not an issue. Water, however, in this case, water forms as a liquid and then instantaneously turns into a gas. So we're going to treat it as a gas because it makes our lives easier. Now, I'm going to say that I'm going to draw carbon as a square, and I'm going to draw hydrogen as a triangle. And I'm going to draw oxygen as a circle because why not? Okay. Circle. Okay. So when I draw CH4, I got to draw 2 units of CH4 as a gas, so they're not going to be touching and they're going to be disorganized. So they'll look something like this. and we will connect them with a line. We have 4 units of oxygen, so that's going to look something like this. They're spread out. Bond those things together. And we're going to draw the 2 gases in this box, spread out, and all the things. We have 2 carbon dioxide, so we're going to deal with that first. So I'm going to put a square here, maybe a square here with oxygen, 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 and we're going to bundle those together with a dash. We have 4 units of water, so I'm going to do that one next. And to the water, I'm going to bond some triangles. Those are my hydrogens. And it's done. Now, we've already said that this is specifically a combustion reaction. Okay? And so a combustion reaction, we need to talk a little bit about what that tells you or what that means, right? So in a combustion reaction, you always start with a hydrocarbon, which is hydrogen and carbon bonded together. And it's always in the presence of oxygen. Always is. Those are the 2 things that you have for every combustion reaction. Now, the generic formula template is going to be something like CX HY plus O2 will 100% react to form CO2 and H2O. Now, that's my generic template, and I'm going to kind of use that template to figure out the rest of my life here in this particular reaction. So I have my CX, so C4. I have my HY, so H10, plus the O2, that's a thing. It's going to react to form the CO2 and the H2O. Now, all that I'm going to do is I'm going to line up the things on my product side that need to be there. So it should be no surprise that we are going to have CO2 as a product and water as a product. And so because that is the situation, I need to still balance this. So I'm going to go and do that. So we're looking at the relationship between carbon, hydrogen, and oxygen on both sides. On the left side, reactant side, I have 4 carbons, 10 hydrogens, and 2 oxygens. On the right side, the product side, I have 1 carbon. I've got, oh, look at that little sneaky guy, 3 oxygens and 2 hydrogens. Oxygen shows up 2 times on the right side. It's a little sneaky. Now, to balance this, I'm going to start by checking to make sure that my carbons are balanced. So I've got 4 carbons on the reactant side. I want 4 on the product side. So I'm going to put a coefficient of 4 in front of CO2. That gives me my 4 carbons, but it also gives me 8 plus 1, which is 9 oxygens. Going to continue balancing. I'm going to try to balance my hydrogens. I have 10 on the left, the reactant side. I need to get 10 on the right, the product side. So I'm going to put a coefficient of 5 there, which will give me my 10, but 5 times 1 is now 5. 8 plus 3 is no longer 9, but it's 13. So I do want to balance this the easy way. So I'm going to divide 13 by 2, and I'm going to get 6.5, and I'm going to throw a 6.5 right there. And everybody's balanced. But you can't have a part of an oxygen. You either have oxygen or you don't. You don't get like 0.5 oxygen. So when that's the case, what we have to do is we have to double all of the coefficients. So I'm going to get a 2, a 13, an 8, and a 10, and this thing is going to be balanced. Done. Questions about the 5 different types of reactions. We learned about a single replacement. We learned about a double replacement. We learned about a synthesis reaction. We learned about a decomposition reaction. And then we learned about a combustion reaction. All right. That's as good of any place to stop. So let's talk about your homework.